In this chapter, we're going to talk about something called eigenvalues and eigenvectors, and we're going to see how eigenvalues and eigenvectors can be used in different places. And one of those places is actually differential equations, where we can solve a system of differential equations. So let's start with a few definitions. Let A be an n by n matrix. I want you to notice that first that this guy has to be a square matrix. The scalar lambda is called an eigenvalue of A when there is a non-zero vector x such that Ax is equal to lambda x. The vector x is called the eigenvector of A corresponding to lambda. So lambda is just a scalar value. Okay, it's just a plain old number, and that's called the eigenvalue. So what's happening here is we have an n by n matrix. X is always going to be a vector, so this is going to be an n by 1. I'm going to view it as a column vector. Now, when we multiply these two together, notice we're going to get an n by 1 vector, so it's going to give us a column vector. We're looking for a scalar value x, so that when I multiply a times x, then I get the same thing as lambda times x. So how do we go about solving that? Well, if we want to solve this, and we know x is also an n by 1, then we can kind of think about it this way. That's got to be equal to the 0 vector. Remember now, this guy's an n by 1, and this is an n by 1, and I can subtract two n by 1 matrices. So I could also think about this way. I have ax minus lambda times ix is equal to 0. So notice all my multiplication is going to work here. I have an n by n matrix A. X is an n by 1. That guy is going to produce an n by 1. Lambda is just a scalar value, but we're going to let I be an n by n matrix. So it's going to be the same dimensions as matrix A. And X is going to be an n by 1 matrix. So that, once again, I'm getting an n by 1 matrix here also. Now, the reason I'm going to view this way is because the only way that I can subtract these two is if the dimensions are the same. And I'm going to think about this idea of, and I'm going to use this term loosely, factoring out this x. So I can kind of view this way. A minus lambda I x is equal to 0. In a sense, I'm factoring out that vector, but I can only do that if that subtraction is still defined in that previous step. Now, we already said that this guy can't be equal to 0, right? Non-zero vector x. So the only way that this could be equal to 0 is if this guy is equal to 0. So then that must mean that the way we're going to find this value that's called an eigenvalue is to take A minus lambda I and then set that equal to 0. And it turns out that when we do this, we're actually going to find the determinant of this matrix and set it equal to the number 0. And that's going to give us our eigenvector, our eigenvalues. When we do this equation that we're going to come up with is called the characteristic equation. Now, once we find the eigenvalues, we can plug those back into A minus lambda I, and we can find essentially the null space of that. And that's going to give us eigenvectors that's associated with that eigenvalue. If we put all those eigenvectors together along with the 0 vector, then that forms the eigenspace of lambda. So let's look at Theorem 7.2, and then we'll look at a few examples. So we're going to let A be an n by n matrix. The eigenvalue of A is a scalar value where the determinant of lambda I minus A. Now, it doesn't matter whether we do it that way or A minus lambda I. Either way, we're going to get the same values for lambda. And then we're going to find those values. We're going to plug them back into this matrix. We're going to do some Gaussian elimination, and that's going to give us eigenvectors corresponding to that lambda value. So we're solving this system, which is essentially the null space. And like we said before, this determinant is called the characteristic equation. I do like to think about it as A minus lambda I instead of lambda I minus A, just to make the computations not necessarily easier. They're going to be relatively the same, but that way I don't have to think about distributing a negative, and you'll see what I mean in this example. So let's look at an example. So let's say we're looking at matrix 2, 0, 0, negative 1. And we want to find the eigenvectors and eigenvectors. Eigenvectors and eigenvalues, excuse me. So we need to find the determinant of A minus lambda I. So we have A minus lambda I. I is the identity. So that's going to be 2, 0, 0, negative 1 minus lambda 0, 0, lambda. And that's going to give us 2 minus lambda 0, 0, negative 1 minus lambda. Now, I want to pause here and show you why I like to do it this way. If we were to do it lambda I minus A, you'll get the same eigenvalues. But look at what's happening. So we're going to have lambda 0, 0, lambda minus 2, 0, 0, negative 1. So that's going to be lambda minus 2, 0, 0, and lambda minus negative 1 is a positive 1. So for me, do you see how the signs in A were flipped here versus here? Once you've done this a few times, it'll be really easy to go from this guy to this guy. But if you go from this guy to this guy, you have to remember to flip the signs of A. A started out being a positive 2, now it's a negative 2. A started out being a negative 1, now it's a plus 1 there. So it's just harder for me to keep up with. But notice we're going to get the same characteristic equation either way. So let's show that. You move this guy down so I have a little bit more room. So characteristic equation. We got to find the determinant of this 2 by 2 matrix. So it's AD minus BC. So now we have 2 minus lambda times negative 1 minus lambda. That's going to be equal to 0. Now, this guy's already factored, so I can just set each factor equal to 0. So 2 is equal to lambda, and negative 1 is equal to lambda. Now, just to show you how this will compare to this one, it's not necessary to FOIL this out, but I am going to so you can see it. If I were to FOIL this out, I would get negative 2 minus 2 lambda plus lambda squared is equal to 0. So we would have lambda squared minus lambda minus 2 is equal to 0. There's our characteristic equation. And then we would solve it and we would still get these guys. If we were to do it with lambda I minus a, I want to show you you're going to get the same thing. So this determinant, same thing, AD minus BC is equal to 0. So we would have lambda minus 2, lambda minus 1 equal to 0. Already factored, right? So lambda is equal to 2 and 1. Just kidding, I dropped a sign here. This is lambda plus 1. So it would be 2 and negative 1. So it's the same thing that we got up here. Now, that characteristic equation, I want to show you how that's going to be the same. If we were to distribute through, we would get lambda squared plus lambda minus 2 lambda is a minus lambda minus 2. So you're going to get the same characteristic equation either way, or you'll be able to manipulate it so it's the same. Sometimes there will be opposite signs, but you could factor a negative 1 out and then divide both sides by negative 1. Either way, you'll get something that's the same here, and you will always get the same eigenvalues here. But like I said, I just prefer this. It just makes it easier to compute super, super fast if I snap my fingers. So we've got 2 eigenvalues, 2 and negative 1. Now let's find eigenvectors. Eigenvectors. I can't talk today. So remember what A minus lambda I looks like. In our case, A minus lambda I was 2 minus lambda 0, 0, negative 1 minus lambda. So when lambda was equal to 2, we will have 2 minus lambda, which is 0, 0, 0. Negative 1 minus 2 is a negative 3. Now, we always want to set this equal to 0 to solve. So if I set that equal to 0, I have this. You can kind of think about it like the null space. We're going to do RREF. And when we get to do RREF, we get this. So this says x2 has to be 0, which means x1 can be anything. So our eigenvector, we can think about it as x1, x2 is 0. But we really don't want to include the variable. So our eigenvector will be the vector 1, 0. So why is this the eigenvector? Because it satisfies the definition where AX is equal to lambda X. So if we were to check that here, our X is 1, 0. Our lambda is 2. So if we were to multiply this out, we're going to get 2, 0. And you can see how 2, 0 is definitely equal to 2, 0. So this is kind of like a check, if you wanted to check. It's the vector and the value that corresponds to not solving, but satisfying this particular equation. Now, but we did have 2 eigenvalues, so let's find the other eigenvector. So when lambda is equal to negative 1, we're going to plug that negative 1 back into A minus lambda I. So we're going to have 2 minus negative 1, which is 3. And then -1 minus -1. So -1 minus -1 is 0. And remember, we're setting that guy equal to 0 when we do it. When we do RREF, we take row 1 and replace it with 1/3 row 1. So this tells us that x1 has to be 0 and x2 can be anything. So if we were to write that as a vector, we would have 0 and x2. But we could think about it as x2 times the vector 0, 1. And when we talk about the eigenvalue and the eigenvector, we always want the numbers. We do not want the variables included. So we're going to have 0, 1. So remember what this guy satisfies. Satisfies ax is equal to lambda x. So that's the x value and the lambda that would make this a true statement. If we wanted to check it, we could. So if we were to multiply over here on the left, we would get 0 and -1. That is equal to 0, -1. So it does satisfy and give us a true statement. So let's look at another one. Suppose we have the matrix A is equal to 1, -2, 1, 0, 0, 0, 0, 1, 1. And we want to find eigenvectors and eigenvalues. So we need to set up A minus lambda I. So if we were to do that, we're going to get 1 minus lambda, -2, 1, 0, -lambda, 0, 0, 1, 1 minus lambda. Okay, remember what lambda I would look like? It would look like the identity, except we would have lambdas down the main diagonal since we're multiplying by lambda. So what's going to happen is it's really just going to change those entries down the main diagonal if we view it as A minus lambda I. So now we need to find the determinant of this matrix. So to find that determinant, and I'm going to use determinant notation now. I'm going to do a row expansion, and I'm going to expand along, I'm actually going to do a column expansion, expand along the first column. So I'm going to have -1 to the 1 plus 1 times 1 minus lambda. If I take out first column, first row, I'm left with -lambda, 0, 1, and 1 minus lambda. And then I would have 0 times some stuff plus 0 times some stuff. So this gives me -1 squared is a positive 1, so this is going to be 1 minus lambda times this determinant, which would be -lambda times 1 minus lambda minus 0. So this is going to be 1 minus lambda times -lambda times 1 minus lambda. I'm going to satisfy that, simplify. And remember, what we want to do is set this guy equal to 0. Now, this guy's already factored. I do want you to notice this guy has a multiplicity of 2 because that factor happened twice. So if we were to set each factor equal to 0, we get 1 that has a multiplicity of 2. If I set -lambda equal to 0, I'm going to get 0 for lambda. So we have 2 eigenvectors. Let's see how many eigenvalues we have. And I'm going to start with 0. if lambda is equal to 0, and remember what a minus lambda I looks like. Now we're setting this equal to 0. So a minus lambda I was 1 minus lambda, negative 2, 1, 0, negative lambda, 0, 0, 1, 1 minus lambda. Plugging 0 in, we have 1 minus 0, negative 2, 1, 0, 0, 0, 0, 1, 1 minus 0 is 1. And remember, we're taking that, setting it equal to the 0 vector. And when we do RREF, I ended up with this matrix. So this says x1 equals negative 3x3. x2 is equal to negative x3, and x3 can be anything. So we could view this as x3 times the vector negative 3, negative 1, 1. So our eigenvector would be negative 3, negative 1, 1. Now we could actually use any multiple of that, and it would still satisfy ax equals lambda x. Now, if lambda is equal to 1, and we were to substitute 1 into this, we have 1 minus 1 is 0, negative 1, and 1 minus 1 is 0. I'm just talking about the entries down the main diagonal. Let's do some Gaussian elimination. So this says x2 and x3 are 0. x1 can be anything. So our eigenvector would be the vector 1, 0, 0. Now, if we were talking about the eigenspace, the eigenspace consists of all eigenvectors paired with the 0 vector. So for this one, we had two different eigenvalues. We had an eigenvalue of 0 and we had an eigenvalue of 1. So when we talk about the eigenspace, it's a set of all vectors that satisfy this ax equals lambda x. So the eigenspace, I'll use this notation for 0, would consist of every vector that would satisfy this. So it's really going back to the span. Of x3, negative 3, negative 1, 1. Or x3 can be anything. Okay, now notice we will get the 0 vector if x3 is 0, because 0 times negative 3, negative 1, 1 would be 0. So it takes care of, going back to that definition, it takes care of this piece, writing it this way. And then the eigenspace for 1, I'll write it this way, is equal to the span of x1 times the vector 1, 0, 0 for x1 to be any real number. Now, both of these spaces actually form a subspace of R3 in this case. So it would satisfy all of those, the two pieces for subspace definition, where it's closed under addition and scalar multiplication. What I really want to focus on in this section is finding those eigenvalues and finding those eigenvectors. That's super important because that's going to take us into something called diagonalizing a matrix, which is going to take us into being able to solve a system of differential equations.